Hello, everyone. Uh, this lecture will be talking about the GCD, like the greatest common divisor, and the LCM, least common multiple, and like, how to compute them algorithmically, and using the Euclidean algorithm, also the extended Euclidean algorithm that solves what's called the Zeitz identity. So I'll be explaining all of this during this lecture. So first I begin with the definition. So if you have two numbers, A and B, we say the GCD between them is the maximum number it divides the both A and B. So if we call this R, then we have R divides A, R divides B, and some M greater than R, then either it doesn't divide A or it doesn't divide B. So basically R is the maximum number that divides both together. On the other hand, there's the LCM. I got S here. So the LCM is the is the least number that is divisible by both A and B. So it's quite the converse, you can say. So A divides S here, and B divides S. And like if some number is smaller than S, then A doesn't divide S, or B doesn't divide S. So here we can see that it's the smallest number that is like divisible by both A and B. So you can get examples on that. Let's say what's the GCD in 12 and 8. So the greatest number that divides both is 4. The LCM of both is, I think, 24. And so on. So can keep getting other numbers and so let's say for example now 15 and 21. So here the common divisor is 3. Yeah, I can also get the LCM of that is I think 105. And so on. So here we can we can observe a nice observation, which is if we have like the first number is written as 1 times E1, you or make it alpha. And so on. And here we allow 0 powers, because if there's a prime not in the other number, we can say it's in the other number with the power of 0. And this is beta 2 and so on. Okay. for this beta k. So the GCD would be like the minimum of powers, and the LCM would be the maximum. So for example, this usually have a number like is divisible by n, means that so any power of some prime in B is less than or equal the power of the same prime in n. Because when we make a division, we basically just subtract the power of like n minus the power of the same prime in D. Basically, this has to be greater than this in order for the number to still be an integer. So basically, to get a number that divides both n1 and n2, so it has to have a power here that is less than both of like these two powers, and also the power of p2 has to be less than or equal this, both of these, and so on. So the GCD, we can think of it as it's the number, to the greatest EI, so here's E1 that is less than both of these two. So it's basically the minimum number of these two. Here it's minimum of 1 and beta. So basically this is what we have here, and the same goes for all the powers. This is like for the GCD, and for the LCM it's quite the opposite. So we want the minimum power that is greater than both alpha and beta. So basically it's the maximum in case of the LCM. Here call it dash. It's the maximum of alpha and beta. So this is one of the relations between, or one of the ways to compute like the GCD and the LCM. Also, if we know that like we have two numbers, x and y, the minimum x and y is the maximum x and y. This is equal to x and y. So basically, if we multiply the GCD and an m times the LCM and an m, this is equal to n times m. Because here this takes the minimum of both powers, and here for each prime, here's the maximum of both powers for each prime. So using this, we are just adding the powers, so it's equivalent to making this multiplication. So, like to give an example about this, let's say we have n equal to 2 power 2 power 1, and this is 12, and this is 50. So the GCD would be take the minimum of the 1 and 2, so it's 2 power 1, 3 power 0, 5 power 0. So this is the GCD, which is 2. And the LCM between both is this. So we take the maximum of the powers, 2 power 2, 3 power 1, 5 power 2. So basically this is, I think, 300. This is 100, yeah. And so it's 300. So as we can see, if we multiply both of these, it's 600, and also both of these is 600. Because like n times m is 2, and we then add the powers. So it's 1 plus 2, 3 power 0 plus 1, and 5, 0 plus 2, and so this is coming, this we find it in the GCD, and this also in the GCD, and this in the GCD, while this we took in the LCM. And what comes from the n is 2, 1, and 0, and what comes from the m, like the second, so the 50 here is this, or these powers. So as we can see here, like the purple ones are the maximums in the LCM, and the red ones, the numbers I mean here, are the powers in the GCD. And the summation, even though the numbers come from, these exponents come from different numbers, still the summation is the same. So basically that's why we have the GCD times the LCM is actually the product of the two numbers. So here, once we have this, so given that we can compute the GCD, then we can compute the LCM using this formula, or the opposite. We will use the Euclidean algorithm to get the GCD. And then if you want the LCM, we just get it by computing the GCD and get it from this formula here. So the GCD, it has some, let's say, properties. So first, it's symmetric. It doesn't matter which numbers, like the order of the numbers we plug in. Also, we divide by r for both numbers. The GCD is 1, where r here is the GCD of the original numbers. So here, when we take like the greatest common divisor of both numbers from m and also from n, then basically we don't have any remaining common divisor. So the GCD is 1. We also have this notation, what we call like M O N. M and N are co-primes if the GCD between them is equal to 1. And the GCD between like if the GCD between M and N is equal to R, then R divides any linear combination of M and N. So So here this is called a linear combination. It's basically when we take the first number and multiply it by some constant coefficient and the second number by also another constant, and we add them together. So this is what's called linear combination. So if GCD of two numbers is R, then R divides the linear combination. I think here we can see why, because here the R divides the first part and also the second part, because it divides both M and N. We can take R as a common factor in this expression. So basically we can divide by R in this expression. So that's the overall idea. So these are just some basic properties. When we get to the last property, which is more relevant to our algorithm, so it's this one. So the GCD between M and N is the same as the GCD between M minus N and N. So to prove this, basically we call this part the first part is the GCD M and N, and the R2 is the other part. So basically we need to prove that that R1 is equal to R2.